All right, so as I said, we have finished the interior beam sheet. I'm gonna hide these. Now we're on to exterior beam sheet. So something I realized that I made a mistake is well, not a mistake. You can still type in these values into the exterior beam sheet, or what's actually easier is to, because it's the same building, the dead load and live load will not change. It's easiest just to link them into the previous sheet. So what you can do is type equals, click on the interior beam sheet, and click on, it's going to be hard to do it exactly because they have some kind of pop-up there, but try to click on cell B4 and then hit enter. It'll take you automatically back to exterior beams. Do the same thing with the live load. Equals, click on the interior beam sheet and try to work your way around. If it doesn't work, you can't do it, click on C5 and then hit the left arrow key and it'll take you back to B5. All right, it's a little kind of trick. And then hit enter. And then change those, so highlight both of them and change those colors to the blue to indicate that they're formulas that you don't type over. All right, I'm going to change these automatically to the blue. And you see how a bunch of the cells, or not a bunch, but a handful of the cells started to populate already. Okay, we had errors before, now we don't. Last things we need are the lengths. Okay, so we type in equal, click on the interior, and again, you're not going to be able to click on this cell, so here I'm going to click on length here, and then click the right arrow key to go over to the cell that's underneath all that stuff that's in the way. It's an annoying feature of Google Sheets that does not happen in Excel, but because Google Sheets is a web-based platform, I think that's kind of why they do it. And then the width, type in equals, click here, and then click on the 10, and there we have it. And most of our cells have populated now. Not all of them, most of them. Anyone see the error that I made? Something I forgot to do, actually. And again, if you're speaking, I might not be able to hear you unless Sharv and Adrian are chiming in here for me. So, to explain this, we'll go back over to this here. So, remember, for the interior beams, it was an interior beam, so you had half to the left, half to the right. For an exterior beam, you only have, for this example, the half to the right. For this exterior beam, you only have the half to the left. All right, so the width is not actually 10 feet. It is half of that. It's only one half. So click on the 10 and then just up here, click in the formula bar and divide that number by 2. So backslash divide by 2. Because it's only carrying half the load. All right. And we should be able to check that really quickly. The total load is 200 pounds here. That should be the same, but it's when the width is only half, it's the uniform distributed load is 1,000, whereas here on the interior beam it's 2,000. So so we're good. Okay. And all these calculations, all the formulas I pre-did for us. We don't have to just, otherwise it would just be a lot of copy and paste. And inevitably, when you copy and paste, something's going to go wrong. So I just kind of did that for us to avoid any errors. But what we need to do is we just need to pick a beam. And our design value is our F sub x, our plastic modulus. So we're looking for 28.858. So go to the beam table, and it needs to be 28.858. So go towards the bottom. Z sub x needs to be 28.858. We're looking at a pretty small beam here. 10 by 19 is not going to work. 10 by 22 will not. 10 by 26 seems like it'll work. Let's see, can I get one in? That's the 31, so that's pretty low. Ooh, 29, so 12 by 22. That's about as close as I can get, so let's try the 12 by 22. Something tells me the deflection, the shear in the moment, or the plastic modules will be good, but the deflection is going to be off. So it was a 12 by 22 is what I said, if I remember. That doesn't seem right. 12 by 22 shouldn't have 3.7. Something is wrong there. Oh, I see what it is. Okay, so the 12 by 22, see how it should be 29.3, so that helped me catch an error in my code, so all of us are going to have to update this. You see how it grabbed the 3.6, so I used index 20 instead of index 19, so I caught a flaw. So go back here, and all you have to do is if you double click on the 3.7, you can change it from a 20 to a 19. That was an unintentional mistake on my part, because I intentionally chose a beam where it should have had enough plastic modules. That's what I chose it for. All right. So I knew that should have been good, and it wasn't, so that's what helped me catch the mistake. All right, so I'm good on plastic modules. I'm good on shear. And just like last time, it's my deflection that's too much. All right, it's 1.65 inches, and I'm only allowed 1.2. All right, so I got to get a stiffer beam. So head back over here. So 12 by 22. We can just go up a beam to 12 by 26. Let's see if not, we'll do 12 by 30. Let's see, 26, if that works. Almost, not quite. And so we'll go 12 by 30. You can actually type it in if I know the name of it already. All right, and the 12 by 30 works. All right, is that the same beam as I chose over here? No, 12 by 58. Oh, look, hey, the deflection's the exact same. That's interesting. So the 12 by 30 works. I got 3 goods, and it's not over-designed to the point where I'm wasting my money if I were the client. All right, any questions on this page? All right, so if no questions here, then we're on to a girder, okay? So girders are a little bit different than beams, and I'll try to explain why. So first of all, what you should notice is that the beam diagram is different. For the interior beams and exterior beams, they had a uniformly distributed load. And for the girders, there's no uniformly distributed load, it's 2-point loads, okay? So to try to explain why that is, let's try to highlight and look at what a girder is. So the vertical lines are the beams, the horizontal lines, this is a girder. Okay, so the difference is that a beam holds up the floor above it. It holds up this whole stretch of floor. What the girder does is the girder holds up the beams. Okay, so here's a column, right? Take an I-beam, just like what we're designing, and turn it up on its end. That's the column. And then the girder ties into, or gets bolted into, the web of those columns, okay? And then the beam, so like here's two more columns, here's two more columns, and here's another girder. This is an interior girder. And this is an exterior girder. Okay. And it's important to note that if these are two columns, this beam here ties directly into the columns and not the girders, because you can kind of see how the girder goes into the web of the column, but this one, it goes right into the column itself. It does not go into the girder. So the girders only support certain beams. Okay? And so for the interior beam, we have one beam here, a second beam here, a third beam here, and a fourth beam here. So it supports, an interior girder will support 4 beams, at least for our purposes, for our situation. Okay? So you see you have 2 beams that connect at the same point on an interior girder. All right, so you have this beam here tying in, and you have this beam here tying in. And they tie in at the same point. Opposite sides of the beam, but the same point. And you have the same thing going on here. Okay? Does that make sense how the loading condition on a girder is different than the beam? All right. So we need to figure out what the load is that the beams are pushing down onto the girders. All right. So if you're looking, like this is like looking down the face of the girder, right? This is the girder. And here's the beam tying in here. Well, this beam is going to be pulling down there and there, right? What force is it pulling down with? To answer that question, if we go back to either the interior or exterior beams, let's go to the interior beam, because we are dealing with, interior beam, like, because all of these up here are interior beams that are tying into the girders. At the exterior beam, this exterior beam will again tie into the column. So when we're doing this, we don't even need to consider the exterior beams. We only need to look at the interior beams for this information. So if we look at the interior beam, any thoughts what the forces at the ends of the beams will be? Where should we look for that information? I don't need to know the answer in terms of the number. I want to know what tells us the force that is at the ends of the beams. Any thoughts? Look at the beam diagram. Any thoughts? What do you see at the ends of the beams? R sub A and R sub B? Yeah. Yeah, the reactions at A and the reactions at B. Equal and opposite actions, or equal and opposite reactions. So if something is pushing up on the beam here, if you switch your mind frame, when the beam itself is being supported, then the beam is actually pushing down with that at that point. That's where the shear force is. Okay, and underneath of that, R sub A is equal to R sub B is equal to WL over 2, which is also the same thing as the max shear force. So the beams, each beam is pushing down with 24,000 pounds at this end and at this end. All right, so that's where, it's actually already there. I've linked it for you. So, but that's to explain where that number comes from. Load from each beam, shear at ends. Okay, so that's why it is 24,000. All right. Now, remember, at each point, how many beams are tying into an interior girder at each point? 2. Excellent. Thank you. So 2 of them. And so that means the point load at each of these points is 48,000 pounds. All right. Notice how this is, again, an oversight on my part. If it's not formatted with a comma, it can help you to read numbers quicker when they're formatted correctly. You can go to format, number, and if you just use number here, it will automatically put in 2 decimals. If I don't want that extra decimal, I can click on decrease decimal.
How do you decrease the decimal?
You see these arrows, the 0.0. So one of them is decrease, one of them is increase. I always inevitably choose the wrong one and then realize it, then choose the other one. But so also, this is just aesthetics. If you don't like the 2 being over here to the left, you can change it over to the right. Totally just looks. All right, now the length of the girder. Again, the girders are a different direction, and these are not 24 by 24 square bays. It's a 24 for the beam length, but the girder length is 30 feet. Okay? So the girder length is 30 feet. And the distance from the end to the point load, from the end to where the beams tie into. Well, all the beams are equally spaced 10 feet apart. So it's 10 feet. Whoops. You got to be careful to not click on the picture. Click on that cell and then type in 10. All right. And again, most of these calculations are the exact same. A slight difference here in the calculation for the shear because the different beam loading condition. RA equals RB equals P, the point load. And then the max moment, again, a slight difference. The max moment is just P times A. But again, that just came from the beam formulas. But then the nominal moment is just still applying the factor of safety of 67%, so times 1.67. The shear modulus, again, it is the nominal moment divided by the strength of the steel. And so now this is the number that we need to look for our beam. And you see for this one's much higher than what we did for our other beams. In the last 2 beams, it was 57.7, then it was 28.8. Now it's 192. So that's why, again, the girders are supporting the beams are supporting the floor. So that's why a girder will be a much essentially bigger beam because it's a beam supporting a beam. All right, so we need to look for a 192.384. So if we look down through, obviously the 10 buys and the 12 buys aren't going to be enough. So 192. I see a 192 at a 14 by 109. But I know right away that that's probably not going to be enough. I'm going to go up to the 14 by 132 to see if that's going to be enough or if that's going to be too much. We'll see. So the 14 by 132. So I'm going to type in W 14 by 132. Oh, my formulas are bad. Great. So again, it's the index here. I made a mistake when I was doing this. Apparently, I did a 20 instead of a 19 again. So change that 20 to a 19. And now we're good. Okay. So one small mistake, but obviously it's a relevant one. And then we were close on the deflection, not quite. So we need to go up a little bit on the beam size. So 14 by 132 is not enough. Let's see. Let's go 14 by 145. Oops. Getting closer, but not quite. 14 by 159. I'll do that, and then I'll try to show you by 150. I think it was 159. All right, so now we're good. Oh, and we're pretty close actually. 14 by 159. All right. Another thing to keep in mind, I keep on referencing cost, but I haven't explained how beams are usually priced. And structural steel, to the best of my knowledge, it's still done this way. It's done by weight. All right, so it's 159 pounds per linear foot. Okay, so it's pretty heavy. But the beams can get stronger. You can use a beam that weighs less per linear foot, but has a thicker, a larger web. So what I mean by that, if I went up to, oh, well, that's also why I think I'm having an issue here. I wanted I could have done a 16. Okay, let's see. I need a 250. What was it? 250. No, 192 was what I needed. So I needed 192. And so if I'm looking here, 16 by 100, probably not going to give me enough. I could try it. 16 by 192. Apparently that's not a beam. Oh, by 100. Whoops. All right, so yeah, the 16 by 100 was not enough. But if I go to the 18 by 106, let's see if the 18 by 106 will work. W18 by 106. That's good. All right. And I just saved myself some considerable weight, right? Because what was the one from before that worked? The 14 by what? I can't remember. 14 by 159. So I'm going to just type this down here, W18 by 106, just store that information. And then the W 14 by what? 159. All right, so it all still worked, but if I just do a quick little calculation, W14 by 159, so the difference in weight, so is 159 minus 106. This beam is 53 pounds per linear foot cheaper or lighter, and so then multiply that times 30. So each beam is almost 1,600 pounds less, and then or each girder. And then if I just calculate how many girders there are, or just look at how many girders there are, how many interior girders there are 1, 2, 3, 4, 5, 6, 7, 8. is equal to that times 8. So that's 12,000 pounds lighter that this structure will weigh. And then what's the cost of structural steel per pound? How much structural steel weigh per pound? Between 25 cents and 33 cents. Okay, so let's go on let's average that. Let's say 28 cents per pound is equal to that times 0.28. Well, I've saved, by doing that one little thing, I've saved my client $3,500 on this project. Might seem like, oh, who cares? This thing's going to cost, a couple $100,000 to renovate, or $1 million to renovate. But what? It took me a couple extra seconds, and I saved him 3,500 pounds. That was just for this one thing, right? So that's what being a good engineer. They're going to come back to you if you can say, if you cost it out being this, and your competitor costs it out using the heavier beam. They're going to come back to you in the future, because you can optimize not just the structure, but the cost as well. All right. And again, the reason this worked, the reason that a lighter beam can carry just as much and have less deflection is because if I try to show you here, when the web is longer, it's the same as taking this book and trying to bend it. When it's this way, I can bend it nice and easy. When it's turned this way, you try to bend it, it's going to be much harder. And so when it's a small web, you're going to be able to bend it. But if this were to get really, really big, it's going to be much, much harder to bend. Okay. And then, the flanges on the top and the bottom can be smaller, and that's where you're saving the money. You're saving the weight, right? If it's a smaller web, the flanges need to be wider to have the strength. Whereas if it's a bigger web, you can have smaller flanges. Obviously, there's a lot more to it than just that, but just an explanation of how this is working. Okay? And then the final thing is to finish out this exterior girder. Okay? So the exterior girder, it's very similar, again, to the interior girder, but just like the difference between the interior and the exterior beam, the exterior girder is doing a little less work. And to explain why that is, the interior girder, you have 1, 2, 3, 4 beams going into it. The exterior girder only has 1, 2 beams going into it. So it's only got the one beam from one side at each point. Okay? So it's still 24,000 pounds coming in from each side, from each beam, because remember, these are interior beams going into it, but it's only one beam at a point instead of 2 beams, so it's doing half the work. Again, just going to format this better. And then again, the length is 30 feet. And again, the distance from the end is 10 feet. So the plastic modulus that I need is much less. It's only 96 instead of 192. And so I'm looking for 96 now. I'll stick with the 18 because in terms of uniformity, if I can have my interior and exterior girders be the same, then things will just be generally easier. So I needed a 92, if I remember correctly. That's a pretty big jump from 18 by 71 to 18 by 76. Something tells me the 18 by 76 will work pretty well, though. So let's go W18 by 76. Again, that 19 and 20 index. Should have expected that. All right. Good, good, and good. Deflection's quite a bit lower. So it is slightly over-designed. But, you know, there's no in-between for 71 and 76, unfortunately. If there was like a 18 by 73, I'm sure I could go with that. But it is what it is. Oh, sorry. Oh, what? Wait a second. I'm looking at the wrong thing over here. I was looking at I should have been looking at modulus over here. So, wait, I can go quite a bit lower. I could try one of the 18 by 60s. Let's try an 18 by 60 instead. Okay. It went up to 1.39. Remember, I can go up to 1.5, so I can go even lower. That was 18 by 60. Let's try 18 by 55. Let's see if that works. Oh, just a little over. So I was at the best I can get at by 60. And isn't it nice that we can just change this, and instead of having to redo all of these calculations here, the whole point is the sheet does it for us in a matter of a split second. So, okay. And that's it. All right. I'll pause the